Okay, so we went over protein folding in both nonpolar and polar solvents, so I thought it would be a good time to go over a conceptual like question um, that kind of covers the concepts that we just learned about in the previous videos. Okay, so the question here is saying you're analyzing the primary amino acid sequence of two proteins. The results of your analysis are shown below. Protein A, you find it to be have 400 non-polar amino acids, and while it has 100 polar amino acids. So for the most part, protein A, we're going to be saying that it's non-polar, okay? And then protein B, we find that it's mostly going to be uh, polar because it has more polar amino acids, okay? So now it says, which protein would be more likely to fold in a non-polar environment? So you could pause the video and you could think about it. Try to think about uh, the enthalpy and entropy and see which one makes it, if you can see which one would lead to either protein being more likely to fold, okay? So I'm going to go ahead and start answering the question. So when the question is asking you which protein will be more likely to fold in a nonpolar environment, what it's basically asking you is if you're looking at this delta G equation, okay, remember delta G is telling you favorability of the reaction. So it's telling you if the reaction is going to be spontaneous or not. So if I could rephrase the question, what the question is essentially asking is which protein will give you a more negative delta G, okay? So basically, essentially what we're asking is which protein will give you a more negative delta G. And in order to see if a more nonpolar versus more polar protein will give you more negative delta G, we're gonna have to go and analyze the delta H and delta S and see if there's anything that we can adjust between proteins to see if one is more likely to let our protein get folded, okay? So going back to our table and that we wrote out from a previous video of protein folding in a nonpolar solvent, we came to the conclusion that the delta H in a nonpolar solvent is going to be negative because remember we're going to be forming more H bonds in our products, and that was anytime you're forming more favorable bonds in your products, that's going to be a favorable process, and that will give you a negative delta H. Okay, and then we also came to the conclusion that our delta S is going to be negative because our protein is gaining order, and in a nonpolar solvent, we do not have the hydrophobic effect to greatly, we don't break water cages, we don't greatly increase the entropy of the solvent. So in that case, the entropy would be zero. So overall, the delta S would be negative, which is also unfavorable. Okay, so we have either two options here. We could either make the delta H more negative, okay, or what we could do is we could make the delta S a smaller value so that we can basically fool around with that value so that it's not as big of a factor so that we can make the delta H outweigh the T delta S factor in our delta G equation, okay? So essentially what I'm saying is either we can make the delta H more negative or we can make this positive number smaller so that the delta H outweighs it, okay? So looking at it like this, let's see if we can first adjust the delta S, okay? Looking at the delta S, well, let's think about it. Remember when we were talking about calculating the delta S, the only thing that we have to consider for the delta S was the freedom of motion of the protein. So do you think that altering the amino acid sequence from polar to nonpolar will change anything about the freedom of motion of your protein? Well, in reality, irregardless if it has polar amino acids or nonpolar amino acids, as this protein goes from this kind of freely floating molecule into its ordered final protein conformation, we're going to be decreasing that freedom of motion. So there's not really anything we can do for that delta S term, okay? So we're not going to be able to really adjust the delta S. So now let's look at the delta H and see if there's anything over there that we can adjust, okay? So going back to our delta H from the video, notice how we said that, okay, the backbone, we're going from dipole-induced dipole bonds to H bonds. Okay, so that led to a negative delta H because forming H bonds releases more energy, which leads to negative delta H. Hydrophilic R groups also formed H bonds after folding, which again is stronger bonds in the folded versus unfolded state, which is also negative delta H. And then hydrophobic R groups, we basically went from induced dipole to induced dipole, so the delta H was roughly 0. So looking at this, is there anything you can manipulate to make your delta H more negative? Well, let's think about it. The backbone, regardless of whatever protein you have, the backbone is always going to be the same, right? If it's polar versus nonpolar, the backbone atoms are the same. Only the R groups are changing, and that's based on whichever amino acid you have. Okay, so now we can rule out the backbone because they both have the same number of amino acids in their backbone, and effectively their backbones are the same regardless of if it's polar or nonpolar. Okay, so now let's think about this. Well, if I add more hydrophilic R groups, what's going to happen? The more hydrophilic R groups I'm going to have, the more dipole-induced dipole bonds I'm going to break, and the more H bonds I'm going to form. So that means that I'm going to basically release even more energy to make my delta H even more negative. The hydrophobic R groups, what about them? Well, the more hydrophobic R groups I have, it doesn't really change my delta H because I'm breaking the same strength of bonds in the reactants versus the products. So the key idea here is that if I can have more hydrophilic R groups or more polar R groups, I can make my delta H more negative. And if I can make my delta H more negative, okay, remember we said that we can either make this one smaller or make the delta H more negative, we'll get a more negative delta G. So in this case, we can manipulate the delta H, okay? So by adding more polar amino acids, what we can effectively do is create more H bonds. And because we can create more H bonds, we're going to make the delta H more negative, making our protein more likely to fold. So the answer to this question is we will pick protein letter B because it has more polar amino acids. And that way we can, again, effectively increase the delta H or make the delta H more negative to make our protein folding more favorable.